When we talk about arc length of a circle, we're talking about, so let's say here's my circle, and we're talking about, like, let's say from here to here, we're saying if we were to straighten this out, how long would it be? Okay, so in other words, what's that portion of the circle? When we talk about the arc length on a curve, it's the same idea. It's between 2 points. Okay, so in this case, my interval is A to B. If I were to take this curve and straighten it out, how long would that point be? Okay, so we're going to approach this the same way we have with other applications of integrals, where we want to look at what an infinitely thin slice would be, and then we figure out how to represent that infinitely thin slice, and then we integrate that over the whole integral, or over the whole interval, to get the total arc length. Okay, so let's say that I zoom in on a very, very small segment. Okay, and I'm not going to draw it, infinitely thin, obviously, but I'm going to draw it like this. So imagine this is an infinitely thin piece where, as long as we get close enough, we kind of have that local linearity idea. Okay, kind of like how we got the slope of a tangent from a curve. But anyway, so let's say we zoom in super, super close. This change, we're going to call this change ds, okay, for the change in s for arc length. So arc length is going to be represented by s, okay? So s. Remember, s equals r theta is how we do that in when we're talking about of a circle. So that's why I'm using an s. Okay, so ds is, and as long as we get close enough that this is a linear piece, that is the hypotenuse of a very, very tiny right triangle whose length this way is a horizontal change, so dx, and whose height this way is a vertical change, dy. Okay, so what I have is a little right triangle, meaning that ds from the Pythagorean theorem is the square root of dx squared plus dy squared. Okay, so let me go ahead and write that, and I'm going to zoom back out because we don't need to be, super, super close anymore. So our arc length is going to be equal to the sum of all of the infinitely tiny ds's that we would have if we did this all along the entire curve. Okay, so it's going to be the sum of all of the ds's, and we're going to go from 1 to infinity of those. Okay, but we know from our definition of the definite integral that we can write that as an integral. Okay, so we can write that as the integral from a to b of ds, which from the Pythagorean theorem is the integral from a to b of the square root of the quantity dx squared plus the quantity dy squared. Okay, now when we write an integral like this, it's not quite in the form yet that we can evaluate, because one, we have a dx and a dy. We need to have d something at the end, and then everything else needs to be in terms of that same variable, because this is not Calc 3. We're not doing multivariable calc right now. Okay, so what we're going to do is, we know that the derivative, like f prime of x, if this is f of x, f prime of x could also be expressed with Leibniz notation as dy over dx. So what we're going to do algebraically is we are going to divide everything inside the radical by dx squared. Okay, now that's still going to be under the radical, so I'm just going to draw another one down here. So we're dividing everything, let me do that backwards. We're dividing everything by dx squared. Okay, so algebraically, just doing some manipulation, no calc yet, okay, that becomes the square root of, okay, and dx squared divided by dx squared is just a 1, okay, and then here I have dy squared over dx squared. Well, dy squared over dx squared is just dy over dx squared, which we could also write as f prime of x. I'm going to actually do that in the next form, okay. But then when we divide everything by dx squared, we can't just get rid of it, meaning what we're going to do is we're going to factor that to the outside. Well, root dx squared, okay, is the same thing as, like, this piece right here is just dx. So now I have factored out a dx from under the radical, which inside the radical shows up as root dx squared, okay, but it's just a dx when it's outside the radical. Okay, so this right here is our formula for, based on the Pythagorean theorem, is our formula for arc length, okay? And the only thing I want to add to this is I want to rewrite that as f prime. So it's the integral from a to b of root 1 plus, I'm going to write it as f prime of x squared dx. Okay, this is the formula for arc length. Okay, so not too bad, just based on the Pythagorean theorem, but then integrating just like we would with volume and area and all the other stuff we've done. Okay. One note about this is if we are, let's say we have something that's not one-to-one, like let's say we have a parabola that opens sideways and we want to find the arc length from here to here, then we would do the same thing, except it would be f prime of y dy, and then make sure your a and b are also in terms of y. That's not going to show up for you though. These examples are all going to be in terms of x, but it would be a pretty easy switch if we were going horizontally. Vertically. Okay. All right, so let's apply that formula. One thing to be careful of, make sure that you are taking the derivative and squaring it. Sometimes if we do, if we don't write out our derivative, it's easy to think we're doing the derivative and squaring it in one step, but we tend to forget one or the other of those. So my strong recommendation is write f prime first and then square it when you put it into the equation. Okay. So my equation is y equals x to the 3/2, meaning my derivative is 3/2 x to the 3/2 minus 1 is 1/2. Okay, and then that quantity is going to get squared when I go into this formula. So my arc length, and you can use S for arc length, or I believe our textbook uses a capital L. That's the same as limit though, so I tend to use S, but it doesn't really matter. Okay, so that is equal to the integral from 0 to 32/9 of root 1 plus, and remember I need to square this, so that quantity squared is 9/2 x to the, and then 1/2 times, or 1 x to the 1/2 times x to the 1/2 is just x to the first. Okay, so root 1 plus 9/2 x, then I have a dx on the outside. Okay, if you want to write that separately, you would have 9/4 x to the 1/2 squared, and that's where the x to the first comes from. Okay, and so if you're looking and saying, okay, these are kind of gross limits, it actually is going to work out pretty nicely because here I have a very straightforward u substitution. Oh, I'm doing that stupid thing again. Okay. All right, where I'm going to set the inside equal to u. So then du is 0 plus 9/2 dx. I don't have a 9/2 dx, so I'm going to multiply by 9/2 on the outside, or on the inside, and 2/9 on the outside. So this becomes 2/9 times the integral of that whole quantity is u to the 1/2 because of the square root. Du, 9/2 dx is du, and then I do need to plug 0 and 32/9 into my u to get my limits. So 1 plus 0 is 1, and 1 plus, so 32/9 times 9/2, this is why we have kind of a gross number, is because when we do this, we get a very nice 16, okay? And then 1 plus 16 is 17, okay? So then this is 2/9 times my antiderivative would be 2/3 u to the 3/2 from 1 to 17, so we get 4/27 times 17 to the 3/2 minus 1, and I don't really care what 17 to the 3/2 minus 1 is, so we're just going to stop right here, okay? You also could plug this into a calculator if it's calculator active, but like I said, it's not a bad u substitution, okay? This next one, I'm going to go through the setup, and then I would recommend that you pause it, give it a try on your own. There is a little bit of some kind of funky factoring here that happens, so try it and then see if you get the same thing I do. Okay, so first thing I want to do, since I have 2 terms in my numerator, 1 in my denominator, is I'm actually going to reduce that. I'm going to divide. So x to the 4th divided by 6x is x cubed over 6 plus, and then 3/6x is 1/2x. I'm going to write it like this. Or if you want to write it as 1/2 x to the negative first, that's fine. Okay, still remember to take your derivative before you square. So y prime equals, so now this becomes x squared over 2 plus, and this will be 1/2, and then the derivative of x to the negative first would be negative 1 over x squared. So I'm going to do minus 1 over the quantity 2x squared. Okay. Again, can write it with negative exponent if you'd prefer. Okay. All right. So then into my arc length formula, I have the integral from 1 to 3 of the square root of 1 plus, and then I need to take this quantity and square it. Okay, so squaring that binomial, I'm going to get x to the 4th over 4 minus, so I'm going to multiply these two and then double it. So I have x squared over x squared reduces, 1/4 doubled is 1/2. And then this quantity squared is plus 1 over 4x to the 4th. And then that whole thing is under the radical and then a dx. Okay, again, pause it, give it a try, see how it goes. You might find that if you left it as a fraction and did the quotient rule, then it looks a little bit easier to take the square root, or maybe your use substitution is better, but not necessarily. Okay, what I'm going to do is I'm going to combine the 1 and the negative 1/2. Okay, and so this is x to the 4th over 4, and then 1/2 minus 1/2 is a positive 1/2, and then plus 1 over 4x to the 4th. And then hopefully what you notice is that this is exactly the same as the trinomial when we squared this, except for the middle sign is different. Well, if I have just the middle sign being different, then that means I just need to switch my a minus b squared to an a plus b squared. That's what I mean. So a plus b squared would be a squared plus 2ab plus b squared. Well, if I switch the middle sign, or going the other way, I guess, I would have a squared, and then this would be minus 2ab plus b squared. And so now, since I'm going from a negative 1/2 to a positive 1/2, that means that I know that this factors very nicely as the quantity, and then same as this, except different middle sign. So x squared over 2 plus 1 over 2x squared, and then that whole thing squared, okay? Now, why did I factor this? Because now my square root and square cancel. So this is now I haven't done the calculus part yet. This is now the integral from 1 to 3 of x squared over 2 plus, and I'm actually going to move that x squared up to give it a negative exponent. So 1/2 x to the negative 2nd, so that I can then just use power rule, and it's an easy integral. I don't even need to use substitution. So I'm going to get, so x cubed divided by 3, so that's 1/6, or x cubed over 6. And then minus, add 1 there, I get a negative 1. And then divide by negative 1, so minus 1/2 x to the negative 1st. From 1 to 3, plugging a 3 in, I have 1/6 times 27, which reduces to a 9 and a 2, minus 1/2 times 1/3. And then minus, plugging a 1 in, I've got 1/6 minus 1/2. Okay, so simplifying this, we have 9 over 2 minus 1 over 6. Oh, I guess I'm going to have to go back to my 27 anyway, aren't I? Sure, let's do that. 27 over 6 minus 1 over 6, minus another 1 over 6, and then plus 1/2. So, actually, no, I'm going to leave it as 9 over 2. Okay, so 9/2 plus 1/2 is 10, so that's 5, minus 1/3, 2 6 is 1/3, so that's 4 2/3, which is 12, 13, 14 over 3.